going to present you two transnational access. We had one on sound and specialized sound and sound integration in VR, and the other one on rugby training. So once again, this is all about behavioral research. This is, I would say, unfinished work. I hope it's going to go on, and maybe these people will come back to do more research in these key problems in virtual reality as long as you're interested in behavioral analysis. So the first project was on a study on audiovisual integration in VR, virtual reality. Our visitor was Agoston Turok, came from the Institute of Cognitive Neuroscience and Psychology in Budapest, Hungary. And he made this success in September 2012. So I call it the long-term question, because this is once again an unfinished story about how do you integrate sound into immersive displays. So the long-term question is to test the possibility within large, immersive, multifaceted displays like caves, test the possibility to create virtual sound sources with surround systems, which would be, and this is the growl, indistinguishable from real sources. So keywords are multimodal integration, CAVE, the ventriculoquism effect, which is in other terms the fact that you perceive basically sound where you see visual cues, surround systems, and of course specialized sound. One good thing I would say from my point of view of this, once again, basic ground research is Agoston was able to publish this work at ESCOP, which is the European Conference on Cognitive Psychology, just a few weeks ago. Okay, so the experimental study, we basically asked within the CAVE system, our four-sided CAVE system, we asked the participant to point using a fly stick, could be anything, tracked in the direction of controlled stimuli, which were defined by vision and sound. It could be only sound, but I will talk about vision and sound here. And participants had to point toward the direction of the sound sources. So we spent, and as I said before, it is unfinished because we spent much time trying to design something which would fit in the CAVE system, which is, I'd call it a hard system. So we had, as you see on this slide, speakers here, loudspeakers, 7 of them, which were taken from a 7.1 surround system. And we put them, I will show you on the next slide, behind the screen of a cave. They were organized in a circular display with the subject inside the cave, and they were once again behind the cave. So these were sources. We use them in what we call a surround condition, but after many problems we had with this experiment, this is in fact a stereo condition. We use these two speakers only to create surround sound, and the other sources, which were called free field or real sound sources, were this one, and this one. So these were the sound sources. The stimuli were in these positions, and we tested, in fact, two experiments. One in which the stimuli, visual stimuli, were displaced vertically, and the other one where they were displaced horizontally. And once again, the task was to point toward where the sound was coming in situations where subjects saw, for instance, a stimulus here and a sound coming from here, to understand if people were able to disengage from the visual stimuli. So this is the cave system. People, subjects were inside the cave. And as you see here, they use this fly stick to point toward the direction they thought the sound was coming from. This is, and this has been hard work, and I hope we're going to continue in this direction because we spent much time trying to design something which was testable. So this is the 7 speakers here, 6 or 7? 6, yeah, 7. So they were in a circular display behind the cave. Well, so far the results are really not surprising. And what you see here is this is a visual stimulus position from -21 to +21 degrees. When you ask subjects to point toward the direction of the sound, in fact, you have this ventriculism effect. In fact, they point toward the position of the visual stimulus. Whatever or almost, you can see slight differences here, but I won't have time to talk about that. Basically get a visual attraction problem. So visual stimuli location captures sound location, what I said before. And so far, and this is why I say that we need to continue with this type of research, the differences between surround and real sounds are not really significant. We could continue with more complex scenes. As you see here, the scene was quite brutal, I would say, just a blob, okay? So this was our first TNA. The second TNA is also a challenge. So the name is Virtual Environment for Rugby Skills Training. Our visitor was Helen Miles, coming from Bangor, Visualization and Medical Graphics Group and the School of Computer Science in Wales. And this access was provided between March 18 and March 29. We had a pre-access to start working on this project, beginning of March. So the objective is quite challenging. Once again, it's to develop an advanced environment aiming primarily at rugby skills training. This is an interesting project because this is obviously multidisciplinary with computer science involved, sports sciences, and psychology. And of course, we had input from rugby players. And I mentioned that because this was in a project. Particular motivation to contribute to a future Rugby World Cup win by Wales. Okay. Once again, this is interesting that we had already communication at Cyber World in Japan in October just now. We prove that this research is interesting to academics, and we have a long paper under review. When these people came to see us, they had already set up an experiment in Bangor using training rugby ball and using a tracking here, and they were just projecting on the screen. And you have here a subject trying to throw a ball. At this moment, this ball is connected to the wrist by a rope. So the questions they ask is, what is the use of scale 1 as you have in a cave? Is stereoscopy necessary? Is the ground floor necessary? As you can see here, they had just a frontal screen. They needed faster tracking, and we use a Vicon system because the tracking they had was basically working at 60 hertz, and that obviously was not enough to track someone launching, throwing a ball. And they needed improvement of trajectory modeling. They did that. And the basic problem is you want to have someone holding a ball and throwing this ball. And what you want is to have a transition between this actual throwing and the virtual trajectory which is going to follow. And this is where the problem is, in fact, is to have a correct modeling here. So we use our cave in this configuration. You can open it. So we opened it in an L shape. So this is the ground, and this is the 4 screens to give more room to to people. And this is what we did. In fact, we had to track the ball here. You can see the marks here. And what we did, and this is also something which is in progress. We had ropes here on the ceiling and a rope here, and the ball was attached to a rope, and the subject was throwing the ball, which would come back because it was attached to the rope. Okay, and we had basically this tracking area, not more. This is one subject playing with the ball in the cave, and we can see here we had two positions for people launching, throwing either on the left or on the right, and this is a position of the Vicon cameras here. This is actual images from what we did. So we basically asked rugby players from the sports sciences in our university to throw balls at targets, like you can see here. So we had a couple of targets in the virtual environment. And once again, the major difficulty here, but since you want to actually try to train people to throw real balls, is, as you can see, maybe I hope you can see, this is the tracking of the guy throwing the ball. So this was tracked for 1-2 seconds. And this is a virtual trajectory which was extrapolated from this initial measurement. Hope that makes sense. What we find is not really good news. So we had, by the way, a couple of conditions, without or with stereo, without or with projection on the floor, and a couple of starting position. What you can see here is that basically if this is the target distance, the simulated target distance between 5 and 14 or 15 meters. This is actually the thrown distance by subjects. We had 4 subjects here. You can see that this is the 1-to-1 slope. If subjects were perfect, it would follow this slope. You can see that what we get is on average quite flat. And in fact, you even have one subject who was throwing at 4 or 5 meters, whatever the distance. But many subjects, except a few of them, were throwing quite short, let's say. And the problem is that if you see, this is the captured trajectory, this is the computed trajectory, and what people were saying is that they were feeling that the modeling was wrong. They would launch farther than what they saw. This is one problem we have. The conclusions for this research is that participants did not respond well to the perceived distance, with most throws traveling between 6 and 9 meters, irrespective of the actual target distance. Another important result so far is that stereoscopic simulation is not necessary, doesn't change much, and as well as the use of a floor screen. In fact, we didn't see much or no difference at all concerning what the subject did. So we are facing this result at the moment. It could be that the modeling of a trajectory extrapolating for what we measured with the Vicon system to the trajectory is not correct. It can be a possibility. And this is more annoying, because I think this type of research has important impact on training and the use of virtual reality for training. It could be that even if subjects were told once and many times that there was no danger that they would hit the cave walls, they would have maybe what I call in culture careful behavior. They didn't want to throw too strong, too far, because they were concerned that the ball would hit the walls. I can show you one short video to give you an example of. Well, we were quite satisfied with that, but once again, the results show that it's not over yet with this problem.
About the project with sounds and spatial sound, you use a direction tracking system in order to take the direction, but can you handle a location where a more sharp location, because direction is only a direction is not a point, and I guess that in 3D spatial audio system we can provide also the direction and the distance. So were you able to track these kind of issues?
No, we didn't do that. We didn't do that. This is a good suggestion. No, we didn't do that. Then you would have to use a probe. I don't know exactly how to do that. It would be interesting.
Showing a direction is quite easy. After that, to show a specific position could be more complex, I guess, if there is a longer issue. And if you use the cave, you could also add in the visualization displays some visual artifacts which could trick the perception of a sound. So did you measure some kinds of disturbance between sound and visualization perceptions, or did you just check for the direction of the sound? Because I guess that if you put a sound somewhere in one direction and you show an artifact maybe 20 degrees beside the sound, maybe the people will point at the artifact in your, just because they see something which looks like the sound they want to provide. So is there a trick like that, or did you just test the sound direction?
Yeah, well, Agustin is a scholar, is a doctorate student, and he came with very basic questions about how to do psychophysics. So we ended with these blobs, and I think that's much more to do in terms of complexity of a stimulation with environment, because otherwise it's not useful to have a cave to do that. You can do that in a dark room with spots, and that's enough. This is why I was saying that we need to continue this type of research. The second point is you can use also moving stimuli, and it would be interesting also to have moving stimuli. And finally, the main frustration is that in the cave, because of the system itself, you have sound bouncing everywhere. So in fact, it's very difficult to identify where the sound is coming. And this is a major problem in a cave system. And how do you have specialized sound in a cave system? It's a difficult question.
I have three maybe rapid questions on the second project. One about the 60 Hz gesture recognition. You said that it was not enough to measure the... I'm quite surprised about that, because a rugbyman is very fast, but 60 Hz is quite fast also.
It's not enough, and it might be due to the techniques used in the tracking system itself, which is a video system. And at 60 hertz, you lose track. When the subject throws the ball, it goes too fast, and you lose track of the markers. And this is why we need we use the Vicon system at 200 hertz, and even with 200 hertz, sometimes you lose track of the markers.
Yeah. What you need is to measure speed and acceleration, I guess, of several specific points, and mainly the hand.
Yeah, but basically what you get is positions, and if you cannot get enough positions, you cannot compute your trajectory. So you need a maximum of positions to compute the future trajectory.
And was there any disturbance due to the rope itself? Because the ropes maybe is something which is unusual for the rugbymen, to have some ropes. You spoke about the risk to break the walls and to all the glasses for the video projection system, but maybe the rope themselves could provide disturbance.
It does. We try to limit the problems. But it does, even in the fact that the ball comes back, it's unnatural. It is unnatural. And I don't know how to solve this problem. Because what we know is that the player needs to have the ball in his hand to throw it. If the player throws emptiness, it doesn't work as well. So you need to have a ball. Ideally, the ball should disappear, but I don't know how to do it. Maybe we could work with HMD, but this poses other problems. I think this is an interesting problem we have because this is a real case of how you can apply virtual reality research to real problems. Training.
Yeah, I really sure that the perception must be very disturbed, and with HMD, you will have also the weight of the HMD itself on the head.
Yeah, that's another problem.
So that's related. Maybe with new glasses, very light glasses, we will be able to put HMD and to play with HMD. But it's a very interesting experience, and even if it was not with the audience of my friends, it is a very important project also, and very good example of what can be provided by Visionair.